Hello, welcome to the NPTEL online certification course on deep learning. We have started our discussion on the neural network, particularly the feed-forward neural network. And in the previous class, we have discussed about, or we have started our discussion on learning in a feed-forward neural network. We have discussed about learning in a single layer perceptron. In today's class, we will talk about the backpropagation learning in multi-layer perceptron or multi-layer feed-forward network. So, just to recapitulate, what we did in our previous lecture is we had taken single layer neural networks with nonlinearity as well as without nonlinearity at the output. So, when we have considered a single layer neural network with nonlinearity at the output, and the nonlinearity that we have considered was a sigmoidal function as given in the right hand side in this slide. So, this is the sigmoidal function that we have considered, and for such a kind of network, the output of the neuron, which is given as y I hat is equal to sigma of w transpose x, where w is the weight vector at the input side of the neuron and x I is the input vector. So, for training, you remember that we have said that we obtain the training vectors as ordered pairs given as x I, y I, where x I is the feature vector and y I is the class to which this feature vector belongs. And when I have a single output in the neural network or only one neuron at the output layer, actually we are considering a two-class problem. And in two-class problem, this y I can take value of 0 or 1. 0 means it belongs to one class and 1 means it belongs to another class. So, given this, we have seen that the training algorithm or the weight updation algorithm was obtained as w, that is the weight vector, is updated as w minus some eta times y I hat into 1 minus y I hat into y I hat minus y I times x I, where x I is the input vector and y I hat is the computed output and y I is the desired output. It is the class index of the class to which x I belongs. So, this is what we have obtained for a single output with nonlinearity, where nonlinearity was a sigmoidal function. Then we had moved on to single layer network with multiple outputs, and when we have multiple outputs, then obviously I have to consider an weight of the form wij. So, what I have considered is from the input layer, if I take an ith neuron and we have considered that this ith neuron in the input layer is connected to the jth neuron of the output layer through a connection weight which is given by wij. So, training in this case means that I have to find out the optimal values of wij for all values of I and j. So, as you vary the index I, that means I am considering different neurons at the input layer. As I vary the index j, that means I am considering the connection to all neurons in the output layer. And as before, if I consider the output of the jth neuron, which we are putting here as OJ, OJ is a sigmoidal function of theta j, where theta j is nothing but weighted sum of all the input feature components. Or in other words, this is the dot product of wij for all values of I, the vector that I get with the input vector x. And given this, we had defined an error function or a loss function which is half of Oj minus Tj square, where Tj is the target output, or I can say this Tj is nothing but Yj. So, the Tj that we have considered, it is nothing but Yj, that is the actual class belongingness of the feature vector. So, what we need to do is, we need to minimize this error function with respect to Wij, or this loss function with respect to Wij. So, for that, again we are using the gradient descent approach. So, I have to find out what is the gradient of this loss function with respect to the weights. So, I compute del E del Wij, which according to chain rule comes out to be del E del Oj into del Oj del theta j into del theta j del Wij, and if you compute this, this comes as Oj minus Tj into Oj into 1 minus Oj times Xi, and given this, my weight updation rule in this case becomes Wij gets Wij minus eta times Oj minus Tj into Oj into 1 minus Oj times Xi, where Xi is the ith component of the input vector and Wij is the connection weight from the ith node in the input layer to the jth node in the output layer. So, this is the updation rule that we get with in a single layered perceptron when I have number of outputs or multiple number of outputs. Now, let us go to a multi-layer perceptron. So, as we just indicated in the previous class, that when I consider a multi-layer perceptron or multi-layer feed-forward network, then obviously I have to have an input layer which receives the input vector, and I have to have the output layer which tells you the classy or class belongingness of the input vectors. So, if I have say C number of classes, then I will have C number of neurons at the output layer. So, accordingly I will have C number of outputs. And if a feature vector belongs to say class 5, then output of the fifth neuron should be high and the output of all other neurons should be low. In this case, in this particular example, we are assuming that there are k number of layers, where capital K is the output layer. At the input layer, we are considering that this is 0th layer, and we said in the previous class that the neurons in the 0th layer simply passes the input to its output. It does not perform any other function. Whereas, in all the hidden layers, the neurons perform two tasks. Every neuron takes the weighted sum of all the inputs that it receives from its previous layer and then computes a nonlinear function over it, and the nonlinearity that we are considering over here is nothing but a sigmoidal nonlinearity. And if I consider any layer, say kth layer, where this k I represent as a lowercase in lowercase, so every kth layer passes its output to k plus first layer and it receives inputs from k minus first layer. So, every node in the k minus first layer passes output to every node in the kth layer, and every node in the kth layer passes the output to every node in the k plus first layer. Now, coming to the error function or the loss function which we want to optimize while training this neural network, you can easily imagine that we can only compute the error function or the loss function at the output layer, because it is only at the output layer I know what is my target output Tj. The reason being, if I say that a feature vector, a training vector belongs to jth class, I know that Tj should be high or ideally Tj should be 1, and all other outputs except Tj or except the output of the jth neuron in the output layer should be low, or ideally they should be 0. So, this is known, and as the expected output or the ground truth at the output layer is known, I can only compute the error function at the output layer. I cannot compute error function in any of the layers, any other layers. The reason being, I don't know what is the expected output or what is the target output at the outputs of any other layers. And that is the reason all other layers except the output layer and the input layer, of course, are known as the hidden layers, because I don't know what is their outputs. So, given this, now let us see that how we can train this neural network. So, over here the training, unlike in case of a single layered neural network where training was very simple, because I had to update the connection weights from the input layer to the output layer. Now, in this case, the training for the output layer and training for the hidden layers will be slightly different, because I can compute the error at the output layers, and once I compute the error at the output layers, I can backpropagate that error through the gradient descent approach to the connection weights in between this k minus first layer, k capital, that means it is the layer just before the output layer. So, I can backpropagate the error for updation of the weight vectors from k minus first layer to kth layer. But when I want to update any of the weight vectors in between the hidden layers, you find that I can't compute directly what will be the error at the output of any of the hidden layers. So, following chain rule, I have to get the feedback, or I have to backpropagate the effect of the output error that you can compute at the output layer to the hidden layers, and that we have to use for updation of the weight vectors in between the hidden layers following our gradient descent approach. So, let us see how we can do it. So, given this, you find that updation of the weight vectors at the output layer is almost similar to updation of the weight vectors in a single layer neural network where we had multiple number of outputs. So, here again I assume that this capital K indicates index of the output layer. I take a jth neuron in the output layer, and the output of the jth neuron is represented by OJK. And from our previous discussion, you can recollect that OJK is a sigmoidal function. It is the sigmoidal function of weighted inputs weighted sum of the inputs which are coming to the jth neuron. So, that weighted sum of the inputs I am representing as Wij xik minus 1. What is this xik minus 1? This k minus 1 indicates that this is the output of a neuron from the previous layer, that is k minus first layer, and this subscript I indicates that it is the output of the ith neuron in the k minus first layer. So, I take this ith neuron in the k minus first layer. This ith neuron is connected to the jth neuron in the kth layer through a connection weight Wij. So, the weighted sum of all the inputs to the jth neuron in the kth layer is given by Wij into xik. I have to take the sum over I is equal to 1 to mk minus 1, where mk minus 1 is the number of neurons in the k plus first layer. So, this is the weighted sum, and once I have this weighted sum, then I have to compute the sigmoidal function over it. So, the sigmoidal function is given by 1 over 1 plus e to the power minus theta jk, where this theta jk is the weighted sum, and that is the output of the jth node in the output layer, which is OJK. So, once I have this output, I know, because all the vectors that we are feeding to the input of this neural network are the training vectors. So, I know what is my target output at the jth node, because if the sample belongs to class J, ideally Tj should be equal to 1. And this Ojk is the output as computed by the neural network at a particular instant of time known as epoch, that is the different steps of training. So, I compute the sum of squared error, which is given by Ojk minus Tj square, take the summation over all j for j is equal to 1 to mk. Mk is nothing but the number of nodes at the output layer. So, that gives you the sum of squared errors. We take half of this, because as we have seen in our previous class also, that we have to take the gradient descent, and this is a squared error. So, when I take the derivative, when I take the derivative, 2 comes over here. So, that 2 and half that gets cancelled. So, that is the only reason that we are putting a scale factor which is half. So, for updation of the weight vector Wij, what I need to do is I have to take the gradient or the derivative of this error E with respect to weight vector Wij. So, as you take the derivative of the error or squared error with Wij, so this is what we just said, I need to take the derivative del E del Wij, and if I compute this again following the chain rule, I get del E del Wij is equal to del E del Ojk. The reason we are using this chain rule is that E is given as a function of Oj, that is the output. Wij comes indirectly. So, we compute this derivative using the chain rule, that is del E del Ojk times del Ojk del theta jk. So, if you remember that Ojk is nothing but sigmoidal function of theta jk. So, it is del Ojk times del theta jk, and theta jk is the weighted input or weighted sum of the inputs at the jth node. So, that is given by Wij times theta ik minus 1. So, the last component in this chain becomes del theta jk del Wij, and if you compute this, you find that del E del theta jk, we said that one advantage, so del E del Ojk, that simply becomes Ojk minus Tj, because E was half of Ojk minus Tj square. So, del E del Ojk becomes Ojk minus Tj. Then del Ojk del theta jk, Ojk is a sigmoidal function of theta jk, so as given by this expression. So, del Ojk del theta jk becomes Ojk into 1 minus Ojk. We said that the advantage of using sigmoidal function is the derivative becomes very simple, which is of this form, and del theta jk upon del theta jk del Wij simply becomes Oik minus 1, because if I take the derivative of this with respect to del Wij, it simply becomes Oik minus 1. So, if I put this Ojk into 1 minus Ojk into Ojk minus Tj as delta jk, the reason why I am putting this as delta jk will become clear when we go for updating of the hidden layer weights. So, if I put this, then del E del Wij simply becomes delta jk into Oik minus 1, where Oik minus 1 is the output of the ith node in the k minus first layer. And given this, the weight updation rule Wij simply becomes Wij minus eta times delta jk Oik minus 1, where this eta, as we said before, is nothing but a constant which controls the rate of convergence or the learning rate. So, this is how I can update the weights of the output layer, that is the layer between the output layer and the layer just before the output layer. Now, let us see how we can update the weights of the hidden layer. As we said that I can only compute error at the output layers. This is where I can compute the error. But when I am updating the weights at the hidden layer, I cannot compute what is the error at the output of any of the hidden layers, because I don't know what is the target output over here. So, whatever error I compute here, that through backpropagation has to be brought to this particular layer, and in this layer I have to see what is the effect of this error, and using that I have to go for weight updation, again following the gradient descent approach. So, let us see how we can do that. So, for doing this, I assume that initially we have updated the weights between the output layer and the layer just before the output layer. So, which was my k minus first layer. Now, k minus second layer is one of the hidden layers. So, let us see that how we can update the weights between k minus first layer and k minus second layer. Then we can generalize that result that we get, the weight updation rule, to any of the hidden layers. So, in order to do this, what I do is I take a neuron, say pth neuron, in k minus second layer. I take ith neuron in k minus first layer. You see over here that I am just following a chain, because in the previous case I have assumed that from ith neuron in the k minus first layer I have a connection from the jth neuron in the kth layer, and that connection weight was wij. Now, I am going one more layer before k minus first layer. So, in k minus second layer I have this pth neuron, and this pth neuron in the k minus second layer is connected to ith neuron in the k minus first layer, and ith neuron in the k minus first layer is connected to jth neuron in the kth layer. And I am also assuming that this pth neuron in k minus second layer is connected to ith neuron in the k minus first layer through a connection weight which is given by WPI k minus 1. But you remember, as we just said, that I can compute the error only at the output layer. I cannot compute the error in any of the hidden layers. So, my error function or the loss function is still given by E is equal to half Ojk minus Tj squared, j varying from 1 to mk, that is output that I am computing, the error that I am computing at the output of the output layer. So, this is still my error function. So, now in order to update this connection weight WPIK minus 1, what I have to do is I have to take the derivative of this error function E, this loss function E, with respect to WPIK minus 1. It is no more with respect to Wij. So, again I have to follow the chain rule in order to find out that how this error E, which is computed at the output layer, varies with the variation of WPIK minus 1. So, let us apply this chain rule again over here. I will just skip this slide. So, this is what I have to do, and the derivative that I just said, that I have to compute del E del p I k minus 1. So, this is the derivative that I have to take, and following the chain rule you find that I can write this as del E del O I k minus 1 into del O I k minus 1 del W p I k minus 1. And again del O I k minus 1 W p I k minus 1 using the chain rule can be written as del O I k minus 1, del theta I k minus 1, del theta k I k minus 1, del P I k minus 1. So, these two are very simple, because I know that O I k minus 1 is just the sigmoidal function of theta I k minus 1, and I also know that theta I k minus 1 is nothing but W P I k minus 1 O P k minus 2, and you take the summation from P is equal to 1 to M k minus 2. You remember that we are considering k minus second layer. So, number of nodes in the k minus second layer is M k minus 2. So, as these two functions are known, I can easily compute what is del O I k minus 1, del theta I k minus 1, which is nothing but this, the derivative of the sigmoidal function, and del theta I k minus 1, del P I k minus 1, which is simply O P k minus 2, that is this. So, what I am left with is del E del O I k minus 1. So, how I can compute this del E del O I k minus 1? So, over here you find that E is given as we have already said, the error at the output layer, and where O j k is the sigmoidal function of theta j k, and theta j k is nothing but weighted sum of O I k minus 1. So, given this, you find that del E del O I k minus 1, again by chain rule, I can write this as del E del O j k into del O j k del theta j k into del theta j k del O I k minus 1, right? And that simply becomes sum of O j k minus T j into O j k into O j k minus O j k, which is the derivative of this, into del theta j k del O k minus 1 is nothing but W I j k. So, this is W I j k, and del E del O j k is nothing but O j k minus T j. It is O j k minus T j, and that has to be summed over all j. So, it is again varying from j is equal to 1 to m k, and this I can write as, now you can try to recollect, earlier we had written this term O j k minus T j into O j k into 1 minus O j k as delta j k. So, that I put over here. So, that simply tells me that del O E del E del O I k minus 1 simply becomes sum of delta j k W I j k, where you take the summation over j is equal to 1 to m k, that is the total number of nodes of the neurons that you have at the output layer. So, given this, now our weight updation rule of the weights between k minus second layer to k minus first layer simply becomes W k minus 1 W p I k minus 1, that is updated as W p I k minus 1 minus eta times del I k minus 1 into this was the weight updation rule at the last but output layer. So, that was eta times delta I k minus 1 into O p k minus 2. So, this was the weight updation rule between the output layer and the layer before output layer. So, in the hidden layer, I will have a summation term. Here I am putting delta I k as summation of this. As I said that I can generalize this from output layer to any of the hidden layers. So, I am taking any of the hidden layers, say kth layer, at which I can put this delta ik, k is lowercase, means it is any of the hidden layers, that simply becomes oik into 1 minus oik into summation of the contribution error of error term that you are getting from k minus first layer. So, that gives you delta ik, and using this my weight updation rule in the kth layer, that simply becomes wij getting wij minus eta times delta jk times oik minus 1. So, this oik minus 1 is the output of the k minus first layer, the ith node of the k minus first layer. And using this I can update the weights of any of the hidden layers. So, what I have to do is I have to compute this for all values of I, j and k. And while you do that, you have to start from your output layer and then gradually move to all the hidden layers. So, this is what is the weight updation rule or the backpropagation learning algorithm in multi-layer neural network. And you find that here the error function that we have considered is the sum of squared error, or that is also known as quadratic error. So, in our next class, we will try to see that what is the problem that we face with the quadratic error and what sort of remedy we can have. Thank you.